Hello everyone, and welcome. I'm excited to start our journey today with our presentation on gravitation. This is the first slide, so I just want to say how glad I am to have you all here. Today, we'll explore the fascinating forces that keep planets in orbit and shape our universe. We'll cover the basics of gravity, how it works, and its significance in our daily lives. So, let's dive in and discover the secrets of gravitation together. Let's take a quick look at the overall contents of this presentation. We'll start with the fundamental concepts of gravitational force and how they support the law of gravitation. Then, we'll explore how gravity influences satellites, including their energy, velocity, and various types like geostationary and polar satellites. We'll also discuss how gravity affects objects on Earth, such as acceleration due to gravity and the variation in gravitational acceleration at different locations. Additionally, we'll examine the concept of energy in satellites, including their total energy and binding energy. Finally, we'll wrap up with some thought-provoking questions to test your understanding and some concluding remarks. Throughout, I'll emphasize how these concepts are interconnected and vital for understanding satellite motion and gravitational physics. Let's start by discussing the height of a satellite, which is essentially the altitude at which it orbits the planet. This height influences many factors, including the satellite's velocity and the gravitational forces acting on it. Next, we have the escape velocity, the minimum speed an object needs to break free from a planet's gravitational pull. This is a crucial concept when considering space missions and satellite deployment. Moving on, Kepler's law of planetary motion describes the laws governing the orbits of planets around the Sun. These laws help us understand the motion and predict the paths of celestial bodies. Then, there's the time period of a satellite, which is the time it takes to complete one full orbit around the Earth. This period depends on the satellite's altitude and velocity. Related to this is the variation of gravitational force with respect to height and depth. As you move farther from or closer to Earth's center, the gravitational pull changes, affecting satellite behavior. We also classify satellites based on their functions and orbits. Different types serve various purposes, from communication to observation, and their classifications help us understand their roles better. Now, let's look at gravitational potential, which is the potential energy per unit mass at a specific point in a gravitational field. It tells us how much energy is stored due to gravity at that point. Associated with potential energy is binding energy, the energy required to break apart a body into its constituent parts. This concept is vital in understanding the stability of celestial bodies. The acceleration due to gravity is the rate at which an object speeds up when falling under gravity. It varies with location and altitude, but is key to understanding how objects move in space. Orbital velocity is the speed needed for an object to stay in orbit around another. If it's too slow, it will fall back. If it's too fast, it may escape. Finally, the fundamental force at play here is gravitation, the attractive force between two masses. It governs the motion of planets, satellites, and all celestial bodies in the universe. All these concepts are interconnected and form the foundation of understanding satellite motion and planetary dynamics, which are central themes in our exploration of space physics. The rotation of the Earth around the Sun, or that of the Moon around the Earth, can be explained based on this law of gravitation. It's this gravitational force that keeps these celestial bodies in their orbits. For example, the tides in our oceans are caused by the gravitational attraction between the Earth and the Moon. The Moon's gravity pulls on the water, creating the high and low tides we observe. Additionally, the value of g, or the acceleration due to gravity, is a crucial factor in predicting the orbits and the time period of satellites around the Earth. By understanding and applying this law, we can accurately determine satellite paths and times, which is essential for communication, navigation, and space exploration. This evidence supports the fundamental role of gravity in shaping celestial movements and phenomena on our planet. The gravitational force between two bodies is independent of the presence of other bodies. This means that when we consider the force between two objects, we don't need to worry about what's happening elsewhere around them. The force depends solely on the two bodies involved. Next, the law of gravitation holds only for point masses. Essentially, this means that the theory works perfectly when we treat objects as if all their mass is concentrated at a single point. For extended bodies, the situation gets more complex, but for idealized calculations, point masses make things easier. Now, an important aspect is that the mutual gravitational forces between two bodies are equal and opposite. This is Newton's third law at play. If one body pulls on the other, the second pulls back with an equal and opposite force. This symmetry is fundamental to understanding how gravity works. Additionally, the gravitational force between two point masses is a central force. That is, the force acts along the line connecting the two masses, and its magnitude depends only on the distance between them, which we call r. Notice that there's no angular dependence here. It's purely along that straight line. Another key point is that gravity is a conservative force. This means the work done by gravity in moving an object between 2 points is path-independent, and it allows us to define a potential energy associated with the gravitational field. Finally, the gravitational force between two masses is independent of the intervening medium. Whether there's air, water, or nothing in between, the force remains the same. This universality is what makes gravity so fundamental and predictable across different environments. All these features highlight the elegance and simplicity of the law of gravitation, and connecting these points helps us understand how gravity governs the motion of planets, stars, and even galaxies. Let's consider a hypothetical scenario: an elevator freely falling from the North Pole to the South Pole, passing through the Earth's center. What would its motion look like? Well, initially, once the elevator is released, gravity would cause it to accelerate downward. As it moves toward the Earth's core, its speed increases due to the continuous acceleration. However, as it approaches the center, the gravitational force inside the Earth actually decreases because gravity depends on the mass beneath it, which lessens as we go toward the center. Once it reaches the core, where gravity is effectively zero, the elevator would have gained maximum speed. From there, it would start to decelerate as it moves past the center toward the South Pole, slowing down due to the narrow-veering gravitational pull. Eventually, without any other forces acting on it, it would reach the South Pole with the same speed it had at the North Pole, but in the opposite direction. If there's no friction or air resistance, it would continue oscillating back and forth in a kind of ideal harmonic motion. This scenario highlights some fundamental concepts about gravity and motion inside a spherical body like Earth. It demonstrates how gravity varies with position and how it influences free fall. Connecting this to our overall theme, it shows the fascinating and often non-intuitive ways objects move under gravity's influence, especially in idealized conditions. Now, let's talk about the acceleration due to gravity of the Earth. This is a fundamental concept because it explains how objects fall towards the ground when dropped. The acceleration due to gravity, often denoted as g, is approximately 9.8 meters per second squared at Earth's surface. This means that if you drop an object, its velocity increases by about 9.8 meters per second every second, ignoring air resistance. Understanding this value is crucial because it influences everything from how we design engineering structures to how we understand planetary motion. It's also a key factor in physics equations involving motion and forces. Remember, this acceleration isn't just a random number. It reflects the Earth's mass and size, creating a consistent pull on objects near its surface. So, connecting this to the overall theme, knowing the Earth's gravitational acceleration helps us grasp the forces acting on objects and the principles that govern motion in our environment. It's a cornerstone concept that underpins many other topics we'll explore further in this presentation. Let's take a closer look at how the acceleration due to gravity, or g, varies with respect to depth and height. Starting with the variation of g with height, you'll notice that it never actually reaches zero. In fact, as you go higher, g will decrease but only up to a certain point, and then interestingly, it begins to increase again. This might seem counterintuitive at first, but it makes sense when you consider the Earth's gravitational field and how it diminishes with altitude before reaching a minimum and then changing behavior at very high elevations. Now, shifting our focus to depth, when a body is placed exactly at the center of the Earth, the variation of g with respect to depth becomes zero. This is because, at the center, the gravitational forces from all directions balance out, resulting in zero net acceleration due to gravity. Understanding these variations is crucial because they help us grasp how gravity behaves not just on the surface, but throughout the Earth's interior and at different heights. It also ties into our broader discussion on gravitational forces and their dependence on position. Let's explore the concept of the gravitational field. The space surrounding a material body, like the Earth, within which its gravitational force can be experienced, is essentially a force of attraction directed towards the center of the Earth. Think of it as an invisible region where gravity operates. When we place another mass, say a satellite or an object, into this space, it experiences a gravitational force due to its interaction with the Earth's gravitational field. This force causes the object to be pulled toward the Earth. Now, it's important to realize that every mass, no matter how small, actually modifies the space around it. This modified space is what we call a gravitational field. So, in essence, each object creates its own gravitational influence in the space surrounding it. This brings us to a fascinating point. Two bodies can attract each other through this gravitational force even if they are not physically touching. This kind of interaction is known as action at a distance. It might sound a bit mysterious, but it simply means that gravity acts across space, pulling objects toward each other without any direct contact. So, to sum up, the gravitational field is the region around a mass where its gravitational pull can be felt, and this interaction occurs even without direct contact, highlighting the unique nature of gravitational forces in our universe. Now, let's delve into gravitational potential energy. This type of energy is associated with the position of an object within a gravitational field. Essentially, the higher an object is elevated, the more gravitational potential energy it has. Think of lifting a book onto a shelf. You're doing work against gravity, and that work is stored as potential energy. The key point here is that this energy depends on two main factors: the mass of the object and its height relative to a reference point, usually the ground. The greater the mass or the higher the position, the more potential energy is stored. It's also important to recognize that gravitational potential energy is a form of stored energy that can be converted into other types, like kinetic energy, when the object starts to fall. Understanding this concept is crucial because it helps us see how energy is conserved and transferred in various physical systems, from roller coasters to planets orbiting stars. It ties directly into the overall theme of energy conservation and transformation in physics. Let's consider the Earth as a perfect sphere with mass m and radius r, with its center labeled as O now. Imagine throwing a ball straight up into the air. It will rise to a certain height and then fall back down, right? If we give it a little more velocity, it will go higher before coming back. But here's the interesting part. If we throw it with enough velocity, so much that it keeps going and never comes back, that's what we call escape velocity. This is a key concept because it tells us the minimum speed needed for an object to completely break free from Earth's gravitational pull without any additional propulsion. Understanding this helps us grasp how rockets escape Earth's gravity and venture into space. So, escape velocity is essentially the threshold speed needed for an object to escape Earth's gravity entirely, and it's a fundamental idea in astrophysics and space travel. As you can see here, because the value of g, or gravitational acceleration, on the Moon is quite small, the escape velocity is only about 2.38 kilometers per second. This is a key point because it directly affects whether molecules can stay bound to the Moon or escape into space. Now, the thermal velocity of air molecules, that's the speed at which these molecules move due to their temperature, is actually greater than this escape velocity. So, what does that mean? It means that these air molecules are moving fast enough to overcome the Moon's weak gravity and escape into space. And that's exactly why the moon has no substantial atmosphere. Its gravity isn't strong enough to hold onto these fast-moving molecules, so they just drift away over time. This ties into the overall theme of how planetary characteristics, like gravity, influence atmospheric presence. Now, for the question on the slide, why does the moon have no atmosphere? Well, because its escape velocity is too low relative to the thermal velocities of molecules, leading to the continuous loss of any gases that might have been there. The world's first satellite was Sputnik 1, a historic milestone in space exploration. It marked the beginning of an entirely new era, where humans started to send objects into space to gather information and expand our understanding of the universe. Now, satellites come in two main types. First, artificial satellites, which are man-made. An example of this is Chandrayaan, India's lunar mission, which was designed to explore the moon. These satellites are built by humans to perform specific tasks like communication, navigation, or scientific research. On the other hand, we have natural satellites. These are celestial bodies created by nature, like the moon, which orbits the Earth. They are not man-made but are essential parts of our solar system. And at the core, a satellite is simply a body that continuously revolves around a much larger body in a stable orbit. Whether natural or artificial, satellites play a crucial role in connecting us to the universe and helping us gather vital information. Imagine a tall tower, with its top just reaching outside the Earth's atmosphere. Now, if we throw a body horizontally from the top of this tower, what do you think happens? As we increase the initial horizontal velocity, the point where the body hits the ground moves farther away from the base of the tower. So, at low speeds, it falls close by, but with higher speeds, it lands much farther out. Now, if we keep increasing that velocity, there comes a point where the body no longer hits the ground, but instead keeps falling around the Earth. It's continuously in free fall, constantly pulled towards the Earth by gravity, but moving forward fast enough that it keeps missing the ground. This state is what we call a stable circular orbit, and the object in this orbit is what we call a satellite. It's essentially falling around the Earth, but because of its high horizontal velocity, it stays in a continuous loop instead of crashing down. This principle of launching a satellite, using high horizontal velocities to achieve stable orbits, is fundamental to how we put satellites into space and keep them there. Now, let's talk about orbital velocity. This is the velocity needed to put a satellite into its orbit around the Earth. Basically, it's the speed required for the satellite to stay in a stable orbit without falling back to the surface or flying off into space. Understanding this velocity is crucial because it ties directly into how satellites are launched and maintained in orbit. It's all about balancing the gravitational pull of the Earth with the satellite's forward motion. When a satellite reaches this specific velocity, it's effectively in a continuous free fall around the planet, which is what we call orbiting. So, grasping the concept of orbital velocity helps us better understand satellite dynamics and the engineering behind space missions. A satellite that revolves around the Earth in its equatorial plane, with the same angular speed and in the same direction as the Earth's rotation, is called a geostationary or synchronous satellite. This means that the satellite stays fixed above the same point on the Earth's surface all the time. It's a special type of satellite because it maintains a constant position relative to the ground, making it ideal for communication and weather observation purposes. The key concept here is the matching of the satellite's orbital period with the Earth's rotation period, which is about 24 hours. By doing so, the satellite appears stationary to observers on the ground. This synchronization is crucial for many applications, as it allows continuous coverage of the same geographic area. So, in the context of our overall discussion on satellite technology, geostationary satellites are fundamental because they provide reliable, constant communication links and data collection from the same location on Earth. All right, let's break down the key points for the necessary conditions for a geostationary satellite. First, it should revolve at a height of exactly 35,930 kilometers. This specific altitude is crucial because it allows the satellite to match the Earth's rotation and stay fixed relative to a point on the equator. Next, the sense of rotation must be the same as that of the Earth, which means it should rotate from west to east. This ensures that the satellite appears stationary to ground observers. Furthermore, its period of revolution around the Earth should be exactly 24 hours, the same as the Earth's own rotation period. This synchronization is what makes the satellite appear to hover over the same spot continuously. Finally, the satellite must revolve in an orbit that is both concentric and coplanar with the Earth's equatorial plane. In other words, it should be in a circular orbit aligned with the equator, avoiding any inclination that could cause it to drift away from its fixed position. Putting all these conditions together, we achieve a satellite that remains stationary relative to the Earth's surface, which is essential for applications like communications and weather monitoring. Let's take a look at some of the key uses of geostationary satellites. First, they're essential in GPS, or Global Positioning System, helping us navigate accurately around the world. They also play a crucial role in studying meteorites and understanding our solar radiation and cosmic rays, which impact everything from space weather to Earth's climate. Additionally, these satellites are vital for weather forecasting. They provide continuous, real-time images of the atmosphere, allowing meteorologists to track storms and predict weather patterns more effectively. They're also used to study the upper regions of our atmosphere, giving us insights into phenomena that affect communication and climate. Speaking of communication, geostationary satellites are fundamental in transmitting radio, TV, and telephone signals across the globe, ensuring we stay connected no matter where we are. Overall, these satellites are a cornerstone of modern technology and science, supporting navigation, weather prediction, atmospheric research, and global communication, all interconnected in our daily lives and scientific endeavors. Now, let's explore the uses of polar satellites. These satellites are incredibly versatile tools for a variety of scientific and practical applications. For instance, they are essential for studying the topography of other celestial bodies, helping us understand their surface features and geological structures in detail. They are also used for spying, which includes surveillance and reconnaissance activities, providing critical information from space. Additionally, polar satellites play a vital role in weather and environmental monitoring. They continuously observe the Earth's atmosphere, oceans, and land surfaces, helping us track climate patterns, natural disasters, and environmental changes over time. A key feature of these satellites is their orbit, which is called a planar or polar orbit. This means they pass over the Earth's poles, allowing them to cover the entire surface of the planet over time. An example of a polar satellite is the Indian Earth Resources Satellite, or IERS, which has been instrumental in collecting valuable data for resource management and environmental studies. Overall, polar satellites are fundamental to advancing our understanding of both Earth and space, making them indispensable for scientific research, environmental protection, and national security. Now, let's take a closer look at the total energy of a satellite. When we talk about total energy, we're referring to the sum of the satellite's kinetic energy and its potential energy in orbit. The kinetic energy is related to how fast the satellite is moving, while the potential energy depends on its position relative to Earth. It's important to understand that in an orbital context, these two energies are interconnected. If the satellite moves faster, its kinetic energy increases, but this also affects its potential energy. Conversely, as it moves farther from Earth, its potential energy becomes less negative, which influences its total energy. This concept helps us grasp how satellites maintain their orbits and how energy conservation plays a key role in orbital mechanics. The total energy remains constant unless external forces act upon the satellite, which is a fundamental principle in physics. Recognizing how kinetic and potential energies balance out gives us deeper insight into satellite behavior and the stability of their orbits. So, in essence, understanding the total energy is crucial for predicting satellite movement and designing efficient space missions. Let's talk about the binding energy of a satellite. When a satellite is in orbit, it's actually held there by the gravitational pull of the planet. The binding energy refers to the amount of energy needed to remove the satellite from its orbit and send it flying away into space. Essentially, it's the energy required to overcome the gravitational attraction holding the satellite in place. This concept is important because it helps us understand the stability of the satellite's orbit. A higher binding energy means the satellite is more securely bound and less likely to escape or fall back to Earth. Conversely, if the binding energy is low, small perturbations could cause the satellite to drift away or re-enter the atmosphere. Connecting this to the overall theme, understanding binding energy is crucial for satellite design and mission planning. It ensures we know how much energy we need to keep satellites in orbit, avoid unintended escapes, and plan for fuel requirements for orbital adjustments. So, in essence, binding energy is a key factor in maintaining the balance between satellite stability and controllability in space. All right, so let's talk about how each planet moves around the Sun. The key idea here is that every planet follows an elliptical orbit, which means their paths are not perfect circles, but elongated ovals. And an important detail is that the Sun is located at one of the two focal points of these ellipses. This shapes the way planets speed up and slow down as they orbit. This is what Kepler's first law, or the law of orbits, tells us. Planets don't move in perfect circles. Instead, they travel along these elliptical paths with the Sun at one focus. Recognizing this helps us understand the precise motion of planets and how gravitational forces influence their paths. Connecting this to the overall theme, it's a fundamental piece that explains the nature of planetary motion and sets the stage for understanding the dynamics of our solar system. Now, let's talk about the law of areas, which is also known as the second law of Kepler. The key idea here is that if you draw a radius vector from the Sun to a planet, it will sweep out equal areas in equal amounts of time. What this means is that the areal velocity, or the area covered per unit time, remains constant as the planet orbits the Sun. This is a really important concept because it tells us that planets move faster when they are closer to the Sun and slower when they are farther away. But the amount of area they sweep out in a given time stays the same. It's a beautiful way to understand how planetary motion is governed by the Sun's gravitational pull. In essence, the law of areas highlights the conservation of angular momentum in planetary motion. It connects directly to the overall theme of Kepler's laws, showing how the planet's paths are not just random, but follow precise, predictable patterns. So this law helps us see that planetary orbits are not only elliptical, but also that their speed varies in such a way that the area swept out over equal time intervals remains constant. It's a fundamental principle that underpins our understanding of orbital mechanics.